Hello, everybody, and welcome back to our second lecture with this course. Actually, this is the first technical lecture. As we mentioned in the zero lecture, the main focus of this course is toward self-powered sensors, and we will start our journey with considering one of the most critical parts of this sensing unit, which is the sensor itself. This will be conducted in terms of two lectures, numbered by lecture 1.1 and lecture 1.2. So let's start now with part number 1 with lecture 2, which is the part lecture 1.1. I hope you can now see my presentation slides. And this 1.1 lecture is under the title of Introduction to Sensors. Okay, so let's do it. Principally, I think all of you know the main definition of a sensor. Maybe during your undergraduate measurement courses or any other electronic course, you have faced such a definition, considering a sensor as a energy transferring unit that transfer some physical phenomena into an electrical signal that can be changed in current, voltage, or maybe resistance. This is the main definition or the general definition of a sensor, maybe 100 years ago. Now, this sensing unit principally was used to sense some environmental physical phenomena, like, for example, temperature, humidity, light intensity, and all these stuff. With the developing of the technology around us, the basic passive sensor turned to be what's called a smart sensing unit. So let's try to focus what is different between a passive sensor and a smart sensing unit. A passive sensor is, based on the previous slide definition, is a passive device that converts a physical phenomena into an electrical signal. One of the very good examples for that, when you just demonstrate a thermocouple, for example. This can be easily found in any electronic component shop. This thermocouple is a metallic head with two wires, as you can see. And this metallic head is connected to the source of temperature and convert this temperature into an variation in the voltage. So whenever the voltage or whenever the temperature change, the voltage and the current change. And this is basically a thermocouple. As you can see, it's totally a passive device without any intelligent point, without any processing, without any communication. Now, and with the developing of the technology, we need to transfer this passive dummy sensor into a complete sensing unit. The term smart sensor unit or smart sensing unit, or the term sensor node, now includes not only the sensor. The sensor become a small part of this unit, but it also includes a processing unit where we convert this voltage into a meaning. Because, for example, whenever you put a thermocouple on a hot plate and you measure a voltage, it's, for example, 25 millivolt. This 25 millivolt is a dummy number which has no meaning. It becomes with a meaning whenever you convert or recalibrate this to 25 millivolt, and you know, okay, this 25 millivolt means that the temperature of this hot plate is 60 degrees Celsius. Now you process this value. Additionally, and as we will discover through our course, most likely these sensors produce a very low voltage, which needs some sort of amplification stages to be processed. A good example here, again, is the mic. Whenever you sense the voltage produced from a mic, from a microphone, you will find that this voltage is very low millivoltage, sometimes it's a micro voltage scale. So again, this is another sort of processing. And as we will have an array, or based on our course, a network of these sensors, then you will need this communication link, or what we can call a transceiver. It can be an RF transceiver, it can be an optical transceiver, can have different waves or different forms of wireless communication techniques. So this is another added block in our smart sensing units. Additionally, as all these blocks, typically the processing and the communication link needs power to be operated, then you need a source of energy. And here the word self-powered sensors starts to appear. So you have to have an energy harvester, or a source where you gain or capture energy. As we mentioned in lecture number 0, that this can be light, can be temperature, can be vibration, can be pressure, and an energy management system or an energy management circuit to make sure that the energy produced equals to somehow the energy consumed. And maybe sometimes you have a buffer, or what we can call a storage, or locally what we call it a battery. So this is the macroscopic view for a sensor, or what we call now a sensor node, or a smart sensing unit. Again, by using the development occurs today technology, as you know, definitely you know that one of the main aspects of the technology is to make these systems consume a minimum area. And this, what we can call the SOS technology, or the sensor on a chip technology. A sensor on a chip technology, or sorry, the SOC technology. The SOC technology, or a sensor on chip, by the way, it is also abbreviated sometimes with the system on a chip, whenever it's a generic term to express any electronic system, but in our case, it's a sensor, so that's why we call it a sensor on a chip. So a sensor on a chip is whenever you can add all these parts, all these components into one chip, so you can have this chip to be plugged in any electronic device and behave as a sensor node, or this can be fixed somewhere whenever you are considering, for example, temperature, humidity sensors, and all these stuff in smart buildings and all these stuff. So this is the most updated technology related to sensors. Again, our main focus today, or in this chapter generally, is this orange block, considering the sensing process. In this part of the lecture, lecture 1.1, we will consider the basic sensing technologies which related somehow to the environmental sensing. And we will consider the most two famous type of sensors, the temperature sensor and light sensors. In the next part, in section 1.2, we are going to consider more toward nanosensing by considering some sort of a biomedical sensing using field effect transistors. So let's now start, or let's now go to the first example to be considered in our case, which is thermoelectrical sensing, or in an easy way, temperature sensing. Okay, so what is a temperature sensor? A temperature sensor is a sensor that senses a physical phenomenon, which is in here case the variation in temperature or the difference in temperature, and can turn this into an electrical signal. In order to consider or to understand the basic temperature or thermoelectrical sensing effect, we need actually to combine two perspectives. The first perspective is some sort of an in-depth physical perspective related to the semiconductor device itself. And the second perspective is somehow toward circuit perspective. This sensor as a circuit element, because if you remember, we just considered that in our case, we are considering a system on a chip. So by the end of the day, each of these blocks will be converted into some sort of analog or digital or mixed analog digital circuit, so that we can, by the end of the day, we can put everything into one chip. So this will be our target for the understanding of the thermoelectrical sensors. Okay, so let's start with the semiconductor part. I believe that the next few slides are typically understood in our undergraduate courses, either solid-state electronics or maybe so you have already seen this slide somehow before in your undergraduate courses, either in solid-state electronics, materials, semiconductors, based on your bio, you have, or your curriculum, you have somehow see this slides before. So this is some sort of just a refreshing or a recalling to some old concepts to be or to refresh these old concepts before going into the main concept of thermoelectrical material. So generally speaking, whenever we are considering a semiconductor material, the main or the most famous way to consider a semiconductor material is by representing its energy band diagram. And the energy band diagram usually is in the form of a valency band, a conduction band, an energy gap, and some sort of a Fermi level, which is typically in the middle whenever there is no doping, or what we can call intrinsic material. At 0 degree Kelvin or absolute 0 Kelvin, there is no source of energy, so all electrons are occupied in the valency band and there is no electron in the conduction band. Whenever there is a temperature, the temperature or the intrinsic temperature inside the material in the form of 3/2 kT, where K is the Boltzmann constant, it starts to motivate electrons to come from the valency band to the conduction band, creating what we call hole. This is a process where intrinsic concentration occur, and you can start having what we can call a free carriers in the material in terms of either electrons in the conduction band or holes in the valency band. But the question is, does these free carriers capable to conduct an electrical current? Actually, the answer is a partial yes. You can have a current from this free carrier, but free carriers itself or free carriers alone will not perform a current, because the definition of the current is dq by dt, or in other words, the rate of a change of the charge with respect to time. So creating a charge, or between quotation, what we can call a static charge, is a first step toward having a current. But there is another step needed, which is related to the carrier transport. This current should be pushed or drifted or biased to move. This carrier should be biased to move in order to conduct an electrical current. So how we can force a carrier to move? Herein, based on the semiconductor theory, we have two possibilities. The first possibility is what we can call the drift current, which is simply known in circuits. Whenever you have a material with some free carriers and you insert a potential, a source of potential, a DC supply, for example, this DC supply, well, the positive terminal will attract electrons to move, and the negative terminal will attract holes to move, and then you have this type of motion for the electron and this type of motion for the holes, and you have current, because now you have a free carriers, and these free carriers move under the biasing of a potential. That's, or this what we call the drift current. The drift current can be mathematically described in a form of the number of carriers moving, either electrons or holes, the unit charge of an electron or hole, and the velocity at which these carriers are moving. The velocity here is directly a function on the potential or the electrical field performed by the battery. So in other words, you can write it in terms of mu n and mu b, which is the mobility of electron and mobility of hole, multiplied by the electrical field in the or caused by the DC source here, which is eta. And this mobility, if you remember, is inversely proportional to the effective mass. So this is a general equation that expresses the current due to electrons and holes as a result of the existence of an electrical potential source performing some sort of electrical field termed by eta. This current can be somehow related as J equals sigma times E, where sigma, of course, is the conductivity. I think you already know this information. And this sigma is due to the free carriers, either in terms of electrons or in terms of holes. And in case of n-type, as you know, electrons dominate. In case of the p-type, holes dominate. This is one of the ways where you can push electrons to, or holes, to move from one side to another. But there is another way or another source of motion for carrier, or another source for carrier transport, which what we call the diffused light. The diffused current. What is a diffused current? A diffused current is a very logical phenomena whenever you have a variation in concentration between two sides of a material. Herein, the variation of concentration is in terms of electrons or hole concentration. So when you have one side of a material with higher concentration rate in terms of electron with respect to the other side of the material, then what we should expect is that current will start to move from the higher concentration region or side to the lower concentration side till we reach a homogeneous concentration across the material. This concentration process, or this diffused current, in terms of electrons or in terms of holes, related to the rate of a change of electrons or holes with respect to distance. Here we have a higher concentration, here we have a lower concentration, so you can find the term dN by dx. If we have a uniform concentration like this case, then dN by dx will tend to 0 and you will not have a diffusion current. But what is interesting actually is this D term, which is the diffusion coefficient. The diffusion coefficient is, based on this equation, is some sort of a proportionality term that indicates the rate of variation of this current. So the higher the dN, the higher the diffusion current for the same dN by dx. And same, of course, for dP. Generally speaking, this is the overall drift diffusion current model for a semiconductor material. And if you remember, you use this model in order to describe the carrier transport nearly in all your electronic devices, starting from PN junctions, transistors, either a PGT or a MOSFET, and other electronic devices, as far as the dimension of this device is somehow in the micro scale. But maybe the question now is, what is the correlation between this model and the thermoelectrical behavior? Let me correlate it in two terms. First, by using what's called an Einstein relation, you will find that this dN and dP are directly functional temperature for a given, as you know, the K and Q are constants. The K is a Boltzmann constant and the Q is also unit charge. So it's a direct relation between the diffusion rate or the diffusion coefficient and the diffusion coefficient and the temperature. So by changing temperature, you basically change this D coefficient and you somehow facilitate the carrier motion between the one side to another. Another important aspect related to the thermoelectrical material. Let's do it when we consider one of the famous junctions you ever seen is the p-n junction. This is a typical p-n junction under equilibrium. As you know, basically, logically, the total current will be equal to zero because there is no source of current motion. You didn't insert any sort of a battery or anything. So basically, when you go to this equation, you'll find that you don't have any source of current, and then the total electron current and the total hole current is equal to zero. And this is what we call a thermoelectrical behavior. But let's see what if. What if you expose this side, for example, which is the P side in our case, the left-hand side, into a high temperature condition? What if you expose this side to a high temperature condition? What is the effect of a temperature in semiconductor? Let's see. We already exposed this before, if you remember. Maybe in our first slide or something like that. Yes, here. Whenever you have a source of a temperature, then this source of a temperature will motivate electrons to move from the valency band to the conduction band to create free electrons in the conduction bands and a hole in the valency band. So simply, whenever you expose this side of a p-n junction into a high temperature condition, you should expect some sort of increase in the carrier generation. And this is, by the way, we call it in semiconductor as a non-equilibrium condition. Whenever you inject more carriers, more electrons and more holes into a material. So simply, after exposing this into high temperature condition, I should expect some electrons to appear here and accordingly some holes to be here. Okay, just wait. But if we remember, electrons, free electrons itself, will not be able to conduct the current. You have to have a source for motion. Herein, this is the source of motion. This, if you remember what we called the built-in potential or the built-in drift. So once you have an electron here, this electron will automatically drift to the other side. And please remember that the number of electrons generated here in the P side is directly proportional to the temperature. Whenever you have higher temperature condition, whenever you have more and more electrons to be generated, and then this starts to, or this current starts to flow. And this is basically one of the concepts where we can use to understand how you can turn temperature variation into electrical signal variation, or into electrons and holes. So now you can see from this example how electrons and holes, or how temperature is turned into current and voltage. And this is a basic understanding or a basic concept on the effect of variation, or the effect of exposing temperature into a p-n junction, and then this p-n junction use the drift, the built-in potential in a p-n junction to drift the generated carrier and to convert it into electrical current. So this is a valid example. If you remember my words, I mentioned that we will consider this temperature sensor, or the thermoelectrical sensing behavior, first from a semiconductor perspective, which is what we do now, and then as a circuit perspective. So our next step now is to consider the semiconductor this thermoelectrical sensing unit from a circuit point of view. See you in the next part.